Now that we've introduced the concept of a sequence, we're going to focus on the most important thing for us anyway, related to sequences, and that is the notion of the limit of a sequence, right? So this is of utmost importance to us. And so let's give kind of an intuitive definition for the limit of a sequence. So intuitively, right, because we're not going to approach it very rigorously. So intuitively, a sequence, and I'll just say a sub n. I won't put any like specific starting value of our index here because actually for a given sequence, it doesn't really matter where it starts when we're talking about the limit. It's what happens in the long run. That's really what's important. So many times, if you want to indicate a general sequence with no specific starting value, you could just do the again that a sub n notation with the braces, but no indication of your specific index. So a sequence a sub n is said to converge, right? Set to converge if the terms of the sequence approach, and again this is the non-technical definition, right? So if the terms of the sequence approached a fixed number, and I'm just going to call that number L, right? As n is made arbitrarily large. So arbitrarily large. That is as n goes to infinity, right? So that's what it means for a sequence to converge. And how we write this, we use the same notation that we use for limits. In fact, this you might recognize as a limit at infinity, right? So important concept there from our first semester of calculus, but this is what we would write now for sequences. The limit as n approaches infinity of a sub n, if this sequence converges, then we say the limit is equal to that specific number, right? So if an L exists, so if L exists, right, we say that our sequence A sub n is a convergent sequence, or that it converges, right? We already said that, but we describe it as a convergent sequence. Otherwise, if we don't have a L, so otherwise, right, A sub n is said to diverge, right? And is called a divergent sequence, right? And that's the big question for us. Given a sequence and our ability to compute limits at infinity, we can determine if a sequence is convergent or divergent, right? And that's the main thing that we are interested in for these sequences. So everything that we need to know to answer this question has already been covered in your first semester of calculus. So we're just essentially doing a review of limits at infinity. So for the rest of this video, let's just work some examples. So Um, we'll just do quite a few examples, right? And the instructions would be to simply determine if each sequence converges or diverges. If it converges, determine its limit, right? So if it converges, oh, let's just say state its limit. All right. So let's just take a look at a couple examples of this. So the first sequence is 3n squared minus 1 over 4n squared plus n plus 3, right? And again, just to emphasize the fact that it doesn't matter what the starting value is. It doesn't matter whether this starts at 0 or at 1 or at 2. Our main concern now is this. What happens to the sequence or the terms of the sequence as n gets arbitrarily large? So n goes off to positive infinity. So it doesn't matter where it starts, is where, if anywhere, does it end up, right? So determining the limit of a sequence, immediately we go to this type of question, right? And with all of the techniques that we have from Calc 1, we have a lot of techniques at our disposal. I'll just go through a few examples that will highlight each of them, right? So looking at this, this is, so the limit at infinity of a rational function. This one is a rational sequence, right? We have two polynomials and they're being divided. There are different things you could do. In fact, let me show you 3 ways you could essentially do this. The first way, the formal way, is for a rational sequence like this, there's always going to be a highest power of n somewhere in this sequence because these are polynomials, and polynomials always have a highest power term. In this case, it will be n squared. If I divide all 5 terms, 2 in the numerator, 3 in the denominator, by n squared, by that highest power, this is what we will get. So if I divide the 3n squared by n squared, I get 3. Divide the 1 by n squared, I get 1 over n squared. And then in the denominator, divide the 4n squared by n squared, I'll get 4. Divide n by n squared, I'll get 1 over n. And then 3 divided by n squared is 3 over n squared. And the reason why this trick helps is because now all the other terms have an n in a denominator, and then I'm left with these 2 constant terms. And all the terms that I have circled here in red, they approach 0 as n gets arbitrarily large, right? So this is like the algebraic trick for evaluating limits at infinity of rational functions / sequences. It doesn't work for any other type of limit. If my n is not approaching infinity, this trick does not work, right? So we end up getting 3 minus 0 over 4 plus 0 plus 0. So this sequence, as n gets arbitrarily large, it converges to a value of 3/4, right? So that's kind of one formal way. Another way is to be able to identify what we call dominant terms. So using the dominant terms approach, dominant terms means that as n gets, again, arbitrarily large, there are terms in an expression that will dominate, meaning they'll be much, 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 much bigger than all the other terms. And in this rational sequence, the dominant terms would be the 3n squared and the 4n squared. Then, I mean, the minus 1 doesn't even change. And even though this n changes, n squared, as n gets very, very large, is much, much bigger than n. So these are what we call dominant terms. And because they dominate all the other ones, again, and this only works for limits at infinity, right? Plus or minus infinity. I can replace this limit with this limit, 3n squared over 4n squared. These are not the same sequence, right? If I were to list the terms of this sequence, they would be very different from the terms of this sequence. But as a limit, right, they both approach the same limit, right? So even though the terms are different, they both get closer and closer to the same fixed number. So once I once I remove the non-dominant terms, then I have something now that is easily simplified, right? So I have 3n squared divided by 4n squared with an n squared common factor, and this is the limit as n goes to infinity of 3/4, and the limit of a constant is a constant. So you see we still get the same 3/4, right? So that's another approach, right? Dominant terms, or you could always say, now the reason I say dominant and not necessarily highest power is because the dominant term approach works for other types of sequences, not just ones involving polynomials, right? But again, there you have to remember a lot of properties in order to identify, okay, which term is going to dominate all the other ones, right? Well, the third approach is radically different, right? And this is good old L'Hopital's rule. Why does L'Hopital's rule apply? Well, because the limit of the numerator is positive infinity. The limit of the denominator is positive infinity. So this is actually of an indeterminate form, right? Infinity over infinity. Right? And again, what we learned previously, it's like previously on calculus. Well, previously we learned that for indeterminate forms, either infinity over infinity or 0 over 0, 0, provided we have differentiable functions, we can apply L'Hopital's. So that limit, let me do my little L'Hopital symbol there. And L'Hopital says take the derivative of the top and the derivative of the bottom separately and then try to evaluate it. So the derivative of the top is 6n. The derivative of the denominator is 8n plus 1. And we still have an infinity over infinity form because as n goes to infinity, so does 6n. As n goes to infinity, so does 8n plus 1. Right? Still can't say anything about it. So the nice thing about L'Hopital's is that it can be applied repeatedly. The derivative of the top now is just 6. The derivative of the bottom is now 8. And we're back to the constant. And look, when we reduce this constant, we get the same constant we had right there. Right? So all three approaches here are completely valid. They're all acceptable, but it is important that you use the right limit notation when you're communicating these ideas. If you're using L'Hopital's, make it clear that you're using L'Hopital's. If you're using dominant terms, make it clear that you're using dominant terms, and you better be clear or better be sure that the terms that you're identifying as dominant terms are in fact dominant terms. And then of course you can use this approach of dividing by the highest power of n. And I would say of the three methods, this is the one that's, I guess, most limiting, because what if it's not a rational sequence like this? In fact, let's look at our number 2, right? So, well, actually, before this, let's just summarize. So this sequence, so this 3n squared minus 1 over 4n squared plus n plus 3, this one converges to 3/4. And what I will make a note about this. Note, there are no terms in the sequence that's actually equal to 3/4. So none of the terms, and if you think about it, it might take a little while for you to think about it and come to the conclusion. None of the terms of this sequence is equal to 3/4. But as n gets very, very large, the terms approach 3/4, right? But the terms approach 3/4 as n gets very, very large. So as n goes to infinity, right? So again, you could try to plug really, really big numbers in, and if you do your exact arithmetic, you will not get something that's equal to 3/4. You will get things that are very, very close, so close that after a while, you know, any device that you're using, it just would probably round to 3/4, but not actually equal to 3/4, right? Again, a subtle but important conceptual difference. All right, let's try another one. Let's see. Here is this sequence, e to the 2n over n, right? And again, I'm not going to put any starting value of our index, right? So this is a simpler looking sequence, but it now involves an exponential function. So let's take the limit as n goes to infinity of e to the 2n over n. And this is another indeterminate form. This is another infinity over infinity form. But there is, because this is not a polynomial, you know, there's no highest power of n or of n that I can use, right? And as far as dominant terms, well, there's only one term in the top and one term in the bottom, and they've already been, I don't know, like isolated, but it's still infinity over infinity. There's nothing I can do with these n's algebraically to cancel anything out. So I don't really have a choice. I have to use L'Hopital's rule in this case, right? So when we take the derivative of e to the 2n, we get 2e to the 2n, courtesy of our chain rule. Today's video is brought to you by the chain rule. And then in the derivative of the bottom, we have 1, so then we end up with this limit. So the limit as n goes to infinity of e to the 2n, and then here we end up with e to the infinity, and again I'll put that in there because again this is not like a number, it's not an expression, just a form that indicates we have the number 2.71 and so forth being raised to a power that's getting large, large, and large, larger, large, large. So that's positive infinity. So this sequence diverges. So this is a divergent sequence, right? So our sequence e to the 2n over n diverges. What this means is we can make the terms as big as we want by making our n as big as we want, right? So if you want this to be you know, 10 trillion, I can find an n that can make it 10 trillion or even bigger, right? So that's the whole idea, is the terms of this sequence are unbounded, right? As n gets arbitrarily large, the sequence just continues to get, the terms just continue to get arbitrarily large, right? All right, so there's that one. Let's look at another one. So this is number 3. So let's say we have the sequence, the natural log of the square root of 1 plus 2 over n plus 3 over n squared. All right. Okay, so that one. So that one has a lot going on. Right? Well, if we're asked to find the limit of a sequence, the next step is always to take the limit as n goes to infinity. Let's see what happens to this the terms. So we have the ln of the square root of 1 plus 2 over n plus 3 over n squared. Well, let's see if we can sort of, simplify this a bit. Now, with the ln and the square root, I know that I can write, in fact, let me write this down. So this is the ln of the quantity of 1 plus 2 over n plus 3 over n squared to the 1/2, right? So just write that square root as the 1/2 power, and we have that property of logarithms that allow us to bring the 1/2 and put it in front of the ln. So this is the limit as n goes to infinity of 1/2 times the ln of 1 plus 2 over n plus 3 over n squared. Right? Now, the thing is, this isn't an indeterminate form. There's no 0 over 0, there's no infinity over infinity. But what this example allows me to do is to remind you of an important property of limits. So if you have a continuous function, right, and we know that the natural log is continuous on for all positive values, right? And now if you look inside here, all these operations will always produce something positive. So since the natural log is a continuous function, I have the ability to take the limit and actually pass it through the ln. So instead of doing the ln of this quantity and then trying to compute the limit, I can actually compute the limit of the quantity and then compute the ln. So like I can switch the order in which I apply the natural log and apply the limit. So instead of doing the limit last, I can compute the limit first. So this is what it looks like. And that's why I say it looks like you can pass the limit through the ln. It's like it has magical powers. It's those magical math powers where you can pass the limit through any continuous function. As long as the function is continuous, right? And you have to think about things like domain, for instance. But once you have this, I can take the limit of the inner part first and see what I get. All right, really useful property, but you have to be clear when it can be used, and continuity is key here, right? All that Calc 1 stuff. So we have the 1/2, the ln, and then look at what we have inside. This is a constant term, and these are those terms like what we saw earlier where you have the denominators that are getting arbitrarily large. So this term approaches 0. This term approaches 0. So we end up with, let me write this down here. So 1 plus 0 plus 0. So it's the natural log of 1. Well, we know what that is. So it's 1/2 times the natural log of 1, which is 0. So as n gets very, very large, the terms of this sequence approach 0. Again, you'll never get it to be equal to 0. The terms will just get very, very close, right? So our sequence (3 over n squared), so that sequence converges to 0. All right. Let's try another one that's a little bit different. So just, to continue the trip down memory lane with all our limit properties, let's take a look at, let's see, which one should we go for? Okay, I won't tell you what it is. We'll just go through it. But let's say you have the cosine of 2n over n cubed, right? So let's say you have that as your sequence. So we want to compute the limit as n approaches infinity of the cosine of 2n over n cubed. Now, the problem with the numerator is that it oscillates, right? Remember, your cosine function oscillates indefinitely with constant amplitude between plus or minus 1. So the top here is what we say is it oscillates indefinitely, so it's oscillatory, right? So this oscillates, right, with constant amplitude. In other words, it doesn't like decay after a while. It just goes between the plus or minus 1 indefinitely. So with constant amplitude. And then the bottom gets very, very large, right? So how do we figure this out? Well, there's that wonderful result from Calc 1 called the squeeze theorem, right? And that's what we're going to use. So I'll show you how the squeeze theorem applies to something like this. So since what we do, and again, we're going to use the fact that the cosine function oscillates between plus or minus 1. So since this is true, right, and this is true for all n, right? Right, so for all n, your cosine function is always bounded between plus or minus 1. What I can do is, clearly, I mean, as n goes to infinity, it's positive, so I can divide each part of this inequality by n cubed. Why am I dividing by n cubed? Because that's the function in the problem. So what I'm trying to do is to get an inequality set up so that I have the limit that I'm trying to evaluate in the middle, and then I would hopefully have easier ones at the sort of towards at the end. So the lower function here, the upper function here, but we're not quite there yet. What I have to do, I have to divide this inequality by n cubed, right? So then I end up with 1 over n cubed is less than or equal to the cosine of 2n over n cubed, which is less than or equal to 1 over n cubed. And the thing is, now these two are easy to compute as n goes to infinity, right? So again, and remember what's required when you're evaluating using the squeeze theorem. We have to evaluate the endpoints separately. So the limit as n goes to infinity of 1 over n cubed, well, that's 0. Right? And then that's also true even if I have a negative in front of it. So the limit as n goes to infinity of negative 1 over n cubed, that's also 0. So by the squeeze theorem, right, the function that's in the middle must also approach 0, right? So by the squeeze theorem, right, probably been a while since you've used the squeeze theorem, right? It's not something that we have to use a lot, but it does come in handy when you have those functions that are bounded and that just oscillates indefinitely. So by the squeeze theorem, the limit as n goes to infinity of the function that's in the middle has to be 0. So if the upper function and the lower function both approach the same number, then the function in the middle is squeezed in between them. So that middle function also has to approach 0. So this sequence, right, converges to 0 as well, right? But in a completely different manner than the one that we did previously. So summarizing our work, so that sequence converges to 0. All right, one more example. So example 5. Let's take a look at the limit. So let's say this is our sequence. 1 plus 1 over n to the power n. Right, so let's say the limit of, as n goes to infinity, of 1 plus 1 over n to the nth power. Now what happens is, again, and this is where you can't treat infinity like a number. Because here we have an expression where you have the n is in the base and it's also in the exponent. The base, as n gets very, very large, this base approaches 1, but then the exponent approaches infinity. And again, you can't just say 1 to the infinity is going to be equal to 1. That fact only works when you have 1 raised to an actual number. Infinity is not a number. This is in fact another indeterminate form. And this is one of the stranger ones, right? Now, in order to use L'Hopital's, it has to be 0 over 0 or infinity over infinity. So I have to convert this using quite a bit of algebra. Let's convert this by converting it to base e. So we're going to use a change of base formula for this exponential function, right? Or what looks like an exponential function. So we're going to use our change of base formula, and we're going to do some algebra off to the side here. So change of base. Well, what base do we want? Well, the easiest base to do calculus in is base e. So if I write this as e and then put an ln there and then put this entire expression there, then it will be equivalent. So if I have e to the ln of the quantity 1 plus 1 over n to the n, then it's exactly the same as what I have here, because the e and the ln are inverse functions, right? And then what I can do, I can use my property of logs and bring that n down, right? So let's write that. So we have e to the n times, oh, I forgot my limit. So we got the limit as n goes to infinity of e to the n times the ln of 1 plus 1 over n. All right. But now, look at the exponent, right? Well, the n is going to infinity, so I have infinity times, and then this part converges to 0, because as n gets very, very large, this approaches 0. I have the ln of 1, so I have this. So I've changed it from 1 to the infinity times infinity to the 0. Well, that's another indeterminate form. I still can't say that this is 0. Just like how I can't say that this is 1, I can't say that this is 0. Because again, infinity is not a number. That fact that 0 times anything is 0, it's true if by anything you mean any real number or any number, right? But infinity is not a number. All right. So what do? Well, to get this, we would like to convert this to 0 over 0. That would be the ideal thing that we could do. And in order to convert it to 0, instead of multiplying by n, I am going to divide by 1 over n. So I'm going to divide by the reciprocal of this. And algebraically, that's the same, right, as multiplying by n. Multiplying by n is the same as dividing by its reciprocal, right? So I can write this as the ln of 1 plus 1 over n over 1 over n. And now this is of the form that I want, because as n goes to infinity, the bottom approaches 0, the top approaches 0, and finally I can use L'Hopital's, right? Not only that, but I can use that other property that I mentioned. The e function is always continuous. So this is what it looks like. I can pass the limit through the e. So instead of doing the e first, I could do the limit first and then do the e after. So it's e to the limit of, and then as n goes to infinity. And then here, let's go ahead and use our L'Hopital's. So when I take the derivative of the top, I'm going to have 1 over 1 plus 1 over n, and then multiply by the derivative of the inner because of the chain rule. When I differentiate the inner function, the 1 over n becomes negative 1 over n squared. And then in the denominator, I have the same thing. When I differentiate 1 over n, I get negative 1 over n squared. So that means the negative 1 over n squared, those factors cancel each other out. And now finally, I think I'm seeing the light at the end of this very dark tunnel. But we have e to the limit as n goes to infinity. And all we have left now is just this, 1 over 1 plus 1 over n. So as n gets very, very large, this term approaches 0. So I'm left with e to the power 1 over 1 plus 0. Right? So we have e to the power 1 over 1 plus 0. So that ends up being e. Magical, right? Not e factorial, just e, like exclamation, smiley face. So what this shows, and again, this I would say is like the trickiest of the indeterminate limits that you'd have encountered in Calc 1. But what this has shown is that this sequence, 1 plus 1 over n to the n, converges to the number e, right? So it converges to e. Fantastic. And on that note, hopefully I've given you a lot to think about in terms of limits. You know, and limits, they're not a throwaway. You know, it's like you want to get through them so you know you can get to derivatives and use your rules and things like that. But no, the limits are the basis of everything we do in calculus, and you can see how important they are when analyzing sequences and determining if a sequence is convergent or divergent. So review your limit properties and have fun evaluating. See you in the next video.